ax equals lambda x is equivalent to a minus lambda I x equals 0. True.
That just makes sense.
Yeah. Yeah, you just manipulate, you can subtract lambda x from both sides, factor out an x, and you get a minus lambda I. Okay, if ax equals lambda x, then x is called an eigenvector. And lambda is called an eigenvalue. So let's look at the notes. The most important thing from today's notes is the definition of an eigenvector and an eigenvalue. Okay, so an eigenvector is a vector x such that ax equals lambda x for some scalar lambda. Okay, any vector, so that if you multiply a matrix A times it, you get a multiple of that vector as the output. The scalar that pops out, lambda, is called an eigenvalue. Okay. This is just a generalization of finding the steady state vector that we did last class. So last class we were looking for x's such that ax equals x, right? And now we're saying now we're looking for x's so that ax equals some multiple of x. Doesn't have to be exactly x. Okay, so ax equals lambda x is equivalent to a minus lambda I times x equals 0. And we say that the set of solutions to that equation, it defines the null space of the matrix A minus lambda I, right? Because those are all the x's that when you multiply that matrix by them, you get 0. It's the definition of a null space. We often call that subspace the null space of A minus lambda I. We often call it the Eigen Space. Okay? And the eigenspace of A consists of the 0 vector and all the eigenvectors associated with lambda. If you are lucky enough to have a triangular matrix, its eigenvalues are its diagonal entries. And no, that's the determinant. That's the determinant. We're just trying to find eigenvalues, the lambdas. The lambdas are just the entries on the diagonal.
So that those entries make a vector.
Those entries, when you multiply them, you get the determinant. Yeah, yeah.
No, what I'm saying is those entries would create a vector like multiplied by.
The diagonal entries?
All these each entry is like.
Yes.
Okay.
And eigenvalue, the lambdas. Lambdas are just scalars. Yeah. Yeah. Yeah, I think you were confusing eigenvector and eigenvalue there. Yeah. All right, so we'll do an activity later to help justify why those are eigenvalues. 0 is an eigenvalue if and only if A is not invertible. Again, we'll do something in the activities to justify that. If V1 to VR are eigenvectors that correspond to eigenvalues lambda 1 to lambda r, then the set V1 to VR is linearly independent. So if you pick any set of eigenvectors that correspond to distinct eigenvalues, makes a linearly independent set. Again, I'll have you do some work in the activities to come up with a reason for that. And then this part, we can use eigenvalue lambda and its corresponding eigenvector x naught to find solutions to the first order difference equations, like ones we discussed in 1.10 and 4.9. So the simplest way to build a solution to x sub k plus 1 equals a times x sub k is to let x sub k be lambda to the k times x naught. And we'll use this a lot more next class. So this was like the very, very end of your 5.1 reading. We'll use it more later. So my first part of the demo was actually to justify that, but I think I'm going to save it because it's pretty theoretical, and what I'd like to do is jump to number 2 first, because it's just more like, let's just think about the definition of eigenvector and eigenvalue. Okay, is 1, 3 an eigenvector for the matrix 1, 6, -1, -4? So let's write down the definition of an eigenvector, right? It's a solution to ax equals lambda x. Okay, x would be your eigenvector. So the question is, does a times 1, 3 equal lambda times 1, 3, equal a constant times 1, 3? So let's see what happens when I put in 1, 3 for my x's there. So I've got 1, 6, -1, -4. That's my A. Replace my x with a 1, 3. Does that equal a constant times 1, 3? So yeah, if I do this multiplication, you could do it in your calculator, or you can just row times column. 1 times 1 plus -1 times 3 is -2. And 6 times 1 plus -4 times 3 is -6. Is -2, -6 equal to a constant times 1, 3? Absolutely, yes. Lambda would be what? -2. That's the answer to part B. The corresponding eigenvalue, right, for that eigenvector is -2. Okay, so this one was a yes. Last class, we were looking for eigenvectors that correspond to an eigenvalue of 1. Yeah. All right, so that makes sense. We're just satisfying the definition of eigenvector here. A times the vector was a constant times the same vector. That makes it an eigenvector. Corresponding eigenvalue is the value of that constant, -2. All right, let's look at another one. So I've got a matrix A, 3, 2, 0, 1. I'm giving you lambda is 3. Is that an eigenvalue? So let's start with the definition again, right? Ax has to equal lambda x. So I've given you lambda, and I have to see, is there an x that will make this true? So I write down 3, 2, 0, 1. That's my A. X I don't know. We'll call it x1, x2 equals, replace lambda with a 3 equals x1, x2. All right, how do I solve that?
We should use our special formula. A minus.
Yeah, we could subtract from both sides. Yeah, for sure. It might actually be easier if I don't put in x1, x2. Let's just write ax equals lambda x to start. Ax equals 3x. Instead of copying down the value of the matrix. If I subtract the 3x from both sides, so I get ax minus 3x equals 0. I can factor out an x, but it has to go on the right because it's multiplication on the right on both of those. So what goes in parentheses here? Definitely an a, right? Minus 3 I, yeah. I is 1, 0, 0, 1, the identity matrix. Because you, it could, why do I have to put an I there? Yes, right. So A minus 3 isn't defined. A is a 2 by 2 matrix. You can't subtract a scalar from a 2 by 2 matrix. Yeah. So this has to be another 2 by 2 matrix. Thank you, Lynn. Okay. So now I just have to calculate A minus 3I. I can do that. So A minus 3I, so 3I would be 3, 0, 0, 3. So I'm going to do A minus that. So I'm going to get 0, 0. 2 minus 0 is 2. 1 minus 3 is -2. So that's A minus 3I times x1, x2. My x is x1, x2 equals, this should be the 0 vector, 0, 0. How do you solve that equation? Augment, row reduce, right? So you end up with 0, 0, 2, -2, augmented with 0, 0. If you row reduce it, you get 1, -1, 0, 0, 0, 0. Okay, so this says that x1 plus minus x2 equals 0, or x1 equals x2, and x2 is free. Yep, so you can pick any two entries for x1, x2 as long as they're the same. What would the simplest choice be? 1 and 1.
The answer is yes.
So the answer is yes. Yeah. Because there is a solution. If there's any solution, then it is an eigenvalue.
Doesn't really matter if we want to just whether if it's consistent.
Right. Yep. So we're just looking to see, is there a solution? Is there a vector so that when you multiply the matrix A times it, you get 3 times it?
So this is one of those ones for like if it's consistent.
Yes. If it's consistent, then lambda is an eigenvalue. All right. So it turns out if I give you an eigenvalue, you're always going to get infinite solutions when you're solving for the eigenvectors, right? If you have an eigenvalue, there are always infinite eigenvectors that correspond to it, okay? And so that makes it a subspace. That makes it a vector space. And we call it the eigenspace. So if I wanted to describe all the vectors that have this solution, right, what do they all look like? Somebody already told me. AA, yeah. So my eigenspace yes, eigenspace for lambda equals 3. Good, thank you. So it would look like the set of all vectors that look like A, such that A is any real number, right? So what would a basis for the eigenspace be? So remember, a basis is a linearly independent set that spans the entire space. 1, 1. So my basis would just have a single vector in it, 1, 1. Because you can just take multiples of that, linear combinations of that one vector. Yeah, it could be 2, 2, it could be 4, 4. Yep.
Well, it's more that it's the other ones, because this one already.
There are infinite choices for the basis, yes. But each basis, no matter if you picked 2, 2 and I picked 1, 1, and anyone else picked 4, 4, right? Like, we could all pick a different basis. There are infinite choices, but every choice has only one vector in it. Okay. Okay, you guys can start your activities. Here. Yeah, coming back. I forgot to come back. Yeah, number 1. Yeah, I gave you a good amount of space there. All right, so I want to show that x to the k equals lambda to the kx naught is a solution to this equation. I've got this equation, x to the k plus 1 equals a x to the k. Okay. I want to show that x to the k equals lambda to the k x naught is a solution. So that means I'm going to come back over here, right? And I'm going to replace my variables on both sides with the solution, right? That's how you check that an equation is true. Yeah, those are vectors. Yeah, because they're bold on your paper. Sorry. Okay, so if x to the k is lambda to the kx naught, what's x to the k plus 1? Yeah, so x sub k is lambda to the k times x naught. So x sub k plus 1 would have to be lambda to the k plus 1 x naught, right? Just replace the k with a k plus 1. All right, does that equal a x to the k? So now I'm going to copy the a, replace the x to the k with lambda to the k x naught. Okay, so I just plugged on both sides of my equation. I replaced the variable x with the solution. So this is how you check if an equation's if you actually have a solution. Plug the solution back in, see if the equation's true. All right, so I'm going to do some manipulation mostly on the right-hand side here. I'm going to pull out lambda to the k. So lambda is a constant, k is a constant, so lambda to the k is a constant, right? And when you're dealing with matrix and vector multiplication, constants can be done at any point. So I'm going to pull it out to the left. So this becomes lambda to the k times a x naught. I just change the order. You can if it's a scalar, right? X to the k is just a number. It's like 5, right? And with scalars, those things are movable, right? Matrices and vectors, you can't change the order, but scalars you can. Okay, the definition of an eigenvector, right? So this only works, this is a way that you build a solution, if lambda is an eigenvalue and x naught is an eigenvector. Okay, so this, I should have added that, right? So it's given lambda eigenvalue x naught eigenvector, corresponding eigenvector. All right, so if x naught is an eigenvector, what does a times x naught equal? Close. Lambda x naught. It's the definition of an eigenvector, right? That ax equals lambda x. So I'm going to replace ax naught with lambda x naught. Yep. What's lambda to the k times lambda? Lambda to the k plus 1. When you like bases, you add the exponents, so you get lambda to the k plus 1 x naught, which is the left side of the equation. So this is basically saying if you have a difference equation, right? This x to the k plus 1 equals ax to the k. That's a difference equation. You can build its solution by looking for eigenvalues and eigenvectors of A, right? So if you can find eigenvalues and eigenvectors of A, you can use them to build a solution to the equation. We will do more with this tomorrow. For now, I want you to work on the activities. They deal mostly with the definition of an eigenvalue and an eigenvector.